All right, so we're going to work through our group work here on section 13.4, motion in space. To start off, we have the path of a particle moving around in the plane. We want to, at each point P and Q, sketch the vectors T and N. And so it says to use the scale from the axes to judge how long your vectors should be. Right, that is talking about these two vectors are unit vectors, and so we want them to have length 1. Right, and so as we move along, T is going to be a tangent to our path and have length 1, so something like that. There is our T there, and then I'm moving over here. Unit tangent looks something like that. Our unit normal is going to point in the direction that we are turning, orthogonal to our unit tangent. So here we're turning to the right, and so it's going to be pointing this way. Again, the unit vector. So trying to have the right length. And here we're turning to the left, and so we'll be pointing this direction. Again, orthogonal to our vector t. All right, part B says, if at the point P we have AT equals 2 and AN equals 1, sketch the vector A. And so here this is going back to the fact that our acceleration vector is always in the plane that T and N define. We just need to go out to AT in our tangent direction and AN in our normal direction. And so here, if we go out 2 in the tangent direction, coming from AT equals 2, and 1 in the normal. All right, we'll get this one right here, and so this will be our acceleration vector if that were the case. Part C, if at the point Q we have AT equals -1, AN equals 1, sketch the vector A. So similar game. AT is -1 though, so instead of moving out in the tangent direction, we'll actually be heading backwards by that length -1. And then in the normal direction by 1. And so up here, right there, and so that's our acceleration vector for at the point Q. All right, moving down. So here we have a vector function, and we want to know its velocity, unit tangent, and the tangential and normal components of acceleration at time 0. And so here to start off, velocity, take the derivative. So velocity, maybe I'll label this at general time t. Taking the derivative, we get 4 e to the 4t, and then 2t. And so at time 0, this will be 4, 4, and 0. Just plug it in for t. All right, next, the unit tangent. We can find that since we just care about what we get at time 0, we can actually just take our velocity vector here at time 0 and scale it so that it's a unit vector. Don't need to find the general form of our unit tangent if we don't want to, at least so far. So here this is going to be v of 0 divided by its size. And so, computing the size here, what do we get? We get 16 plus 16 plus 0 underneath the square root. So, root 32. We could simplify that square root if we really wanted to, but I'll just leave it like that. box our answers here. All right, so that's 2 down here. AT, tangential component of acceleration. Right, that we can get by taking our acceleration vector and dot producting with our unit tangent. And again, we could figure these things out in general for general t if we wanted, but actually since we just care about these things at 0, we can just go ahead and do this for those specific vectors. And so I guess to start, we do need the acceleration vector. So a of t, taking the derivative of our velocity, it's going to be 0, looks like 16 e to the 4t 2. And so our acceleration at time 0 is 0, 16, 2. So that'll be what goes right here in the acceleration. And our unit tangent at time 0, we already know that. And so we can take the dot product of these two things here. 0, 16, 2. Dot product with our 4, 4, 0 vector, scaled by 1 over root 32. And that 1 over root 32, we can just slide that out front. The dot product of these two vectors up top. So we're going to get 0 for the first component, plus 16 times 4, which is 64, plus 2 times 0. So it looks like 64 over root 32. That's our AT at time 0. And last but not least, AN at time 0. So here we have our nice Pythagorean theorem identity for AN. Right, it's the size of a squared. Let me, I'm blanking real quick. I think I know what this is, but let's draw the picture here up in the corner. All right, so this is A, and let's say that our unit tangent is this direction and unit normal is this direction. Then we get this picture, and so here's AT, here's AN. Right, and so, yeah, AT squared plus AN squared equals the size of A squared. And if we want to solve that for AN, just push that over. And, okay, so this is going to be minus AT squared. Okay, that's what I thought. Never hurts to draw a quick picture to remind ourselves what's going on. All right. And we just we need this at time 0, so we can just use our acceleration at time 0 and our AT at time 0 that we found. Sorry for that pause. Here we go. So the size of the acceleration, we're going to have, so it'll be that squared, I guess. So the size of the acceleration is 0 squared plus 16 squared plus 2 squared, which is 4. And we'll be subtracting this over here, 64 over root 32 squared. And so what do we get going on here? Well, the square and the square root cancel off. Left with 16 squared plus 4. That equals 260. And over here we have 64 squared, which happens to be 4,096, and root 32 squared is 32, So if we do that division here, it actually does work out nicely as 128. So at the end of the day, root 260 minus 128, which is root 132. All right, that was the last piece of information we wanted to find. So moving down. So here we're given our acceleration function, and this is meant to mean a of t. I'm going to go ahead and change that on our group worksheets. So we have constant acceleration, and we're told our velocity at time 0 and our position at time 1, and we want to antidifferentiate, work our way back upstream to find our velocity function and our position function, and then we'll find at and an. All right, so here we go. The idea being our acceleration is 0 to 0. Well, our velocity function, right, is going to consist of components whose derivatives give us these three things, right? And so anti-differentiating each component. And so in the first component, something whose derivative is 0 is some constant. Anti-differentiating 2, we get 2t plus some constant. It can be a different constant, so we'll use a different letter. And then something whose derivative is 0 on the right should be some constant. But we can find what those three constants need to be from the fact that velocity at time 0 needs to be 1, 0, and 3. Looking at that, comparing what we have over here, if we plug in 0, so we need our c to be 1. We plug in 0, we'll get 0 over here, so we'll just get d, and so d should be 0, and e should be 3. So 1, 2t, 3 is our velocity function. All right, now from here we can bounce and find our position function. And we're anti-differentiating each component. So antiderivatives of 1 are t plus some constant. Next we'll get t squared plus some constant, and then 3t plus some constant. And I'm just reusing the same letters again. We could have continued on with f, g, and h or something if we wanted to. But anyways, looking at this information, that at time 1 our position is 1, 1, 3. We can see what these need to be. At time 1, we would need to have so 1 plus c equal to 1, and so c has to be 0. And here, our second component also needs to equal 1. We plug in 1, we'll get 1 plus d, and so our d has to equal 0. And then our last component over here, we want that to equal 3 when t is 1. And so when we plug t in 1, we'll get 3 plus e, and so e needs to be 0 as well. And so here is our position function and our velocity. And so last but not least, we need to find our tangential and normal components of acceleration. See if I can fit that in over here. All right, t of t. All right, this is our acceleration dot our unit tangent. So we have our acceleration. It's 0 to 0. We want to dot that with our unit tangent. Unit tangent is our velocity, 1, 2t, 3, divided by its size, square root 1 plus 4t squared plus 9. So we can work out this dot product just between these two vectors, and that'll give us a numerator over this square root, which is 10 plus 4t squared. And so multiplying here, working out this dot product, 0 times 1 plus 2 times 2t plus 0 times 3. Looks like this boils down to just 4t in the numerator. Last but not least, I'm going to fit it an. And we have our Pythagorean theorem formula for this. So the size of our A, we could work it out, but it's actually just purely in the y direction. So the size of A, we can just see it's going to be 2. So 2 squared is 4 minus our AT squared, so that thing squared. And so I guess if we square the numerator and square the denominator, what we end up with is 16t squared divided by 10 plus 4t squared. I'll leave it like that. All right, moving on down. Here we're given an acceleration vector and a unit tangent vector. We want to figure out AT, AN, and our unit normal. Here we have our formulas, and so we'll just start in. AT is our acceleration dot product with our unit tangent. And so working out the dot product here, we're going to get 1/3 minus 4/3. And the last components multiplied, we'll get minus 2. So 1/3 minus 4/3 is negative 3/3, which is negative 1 minus 2, so it looks like negative 3 is what our tangential component of acceleration is. And from our Pythagorean theorem formula, maybe off to the side, we'll do the size of A. Size of A is square root of 1 plus 2 squared, which is 4, plus negative 3 squared, which is 9, and so root 14. And so we are squaring that, so we just get the 14 minus AT squared. Negative 3 squared is 9. 14 minus 9, so root 5 is our normal component of acceleration. All right, now we need to find the unit normal, and I claim that we now have, in a particular puzzle, all but the one piece that we want to find. And that particular puzzle looks like this, our equation that relates our acceleration to our unit tangent, unit normal, looks like the following. Right? AT times unit tangent plus AN times our unit normal. And we know a lot of these different ones. Acceleration is one. You know what, let me not work this out right now. Let's solve for what we want to find, and then I think this will be a little bit cleaner. So if we subtract the AT over, so we have acceleration vector minus AT unit tangent equals AN times N, and as long as AN is not 0, we can divide by it. And so what we get is our unit normal is acceleration minus ATT divided by AN. So here we can start filling in. So our acceleration is 1, 2, minus 3. Subtracting our AT, which is negative 3, times our unit tangent. So 1/3, negative 2/3, 2/3. And then that we're dividing by root 5. And so working this scalar multiplication out, maybe we can take this minus and negative and make that a big plus, and this 3, distribute that in. What we'll get at the end of the day, 1, 2, negative 3. We're going to be adding the vector 1, negative 2, 2. So when we add those vectors, we get, component-wise, we're going to get 2, 0, and negative 3 plus 2 is minus 1. And that's scaled by root 5. Right. And we could leave it like that, or if we really wanted to, we could slide out the root 5 as a 1/5 constant multiple up front. Either way is good to go. All right, that's it for today. See you next time.